Welcome to the Coherent Laser Safety Training video. Before we begin, please note the following copyright laws that govern this program. You may wish to pause this video and may do so at any time. This video presentation will discuss the hazards and control measures associated with the various lasers that Coherent produces. The two hazards that will be discussed are beam hazards that are associated with laser eye safety and non-beam hazards, which include chemical, biological, and electrical types. In addition, it will also be worth mentioning other types of non-beam hazards such as fire and asphyxiation and their respective control measures. While Coherent manufactures all class types of lasers, it is likely you'll be training to use a Class 3 or Class 4 laser. These two laser classes potentially pose the highest hazard, so your undivided attention to this video is paramount. Moreover, you will be required to pass the laser safety exam that concludes this video presentation prior to attending any laser training course that Coherent offers. Coherent and its employees take laser safety very seriously and will ensure that your training is conducted in compliance to the highest laser safety standards. However, for liability reasons, students will be required to sign a laser safety waiver at the beginning of any class. Before we begin, it is beneficial that you acquaint yourself with various laser safety terms and regulations that govern laser products. When we speak of safe viewing the laser beam, it is in terms of MPE or maximum permissible exposure. This value represents the level of laser radiation to which a person may be exposed to without hazardous effects or adverse biological changes within the eye or skin. In discussing laser safety eyewear, an important characteristic is its optical density. Typically, this numeric value is located on the side shield of the frame and represents the amount of transmittance the optical element will allow within a given wavelength. A critical note to this value is that the OD is only specific to the wavelength called out. Therefore, wearing safety glasses for the wrong wavelength can give a false sense of protection. For example, the safety eyewear shown is not rated for a CO2 laser wavelength and may or may not offer protection. Therefore, this pair should not be used for a CO2 laser. The Nominal Hazard Zone, or NHZ, describes the space within which the level of direct, reflected, or scattered radiation during normal operation exceeds the applicable maximum permissible exposure. In basic terms, the NHZ distance represents how far away you must be from a laser without protection. With low-power lasers, this distance is usually quite small. High-power lasers, on the other hand, can exhibit an NHZ of several hundred meters. As with any laser product, there are specific laser safety standards in which Coherent products must comply with. The American National Standards Institute, or ANSI, and the Occupational Safety and Health Administration, or OSHA, govern the safety guidelines for lasers, such as laser classification. To address other safety concerns, these lasers must also adhere to the Code of Federal Regulations, or CFR, CDRH, CE, CSA, TUV, and UL guidelines. Light is comprised of many different wavelengths, and since the laser light is a form of light, a critical characteristic is the specific wavelengths a laser contains. Most lasers operate in the UV, visible, and infrared spectrums. UV or ultraviolet light consists of wavelengths between 100 and 400 nanometers. The next wavelength group is the visible, which consists of wavelengths in the region of 380 to 780 nanometers. Infrared wavelengths are found after the visible range at around 750 to 1000 nanometers. You may notice that there is a slight overlap in the stated ranges. This is due to the differences in each individual's ability to detect the various wavelengths. There are many types of lasers, and all of them fall into a classification system. The lowest class, Class 1, represents no hazard. The second class, which is called Class 1 product, represents no hazard during normal use. This class contains such devices as laser printers and compact disk drives. Class 2 represents visible lasers with up to 1 milliwatt of output power. Momentary viewing of this beam is typically not considered hazardous, since the upper radiant power limit on this type of device is less than the maximum permissible exposure, or MPE, of 0.25 seconds or less. Intentional extended viewing, however, is considered hazardous. Class 3A represents visible lasers with a power range of 1 to 5 milliwatts and can only be viewed momentarily. This category also includes high-power laser pointers. These pointing devices should never be directed at a person's face for obvious reasons. Laser Class 3B contains lasers that have a power range of 5 to 500 milliwatts and pose a hazard from direct and specular reflections. Class 4 lasers are of the highest hazard level, and instantaneous damage can result from direct exposure, as well as specular or diffused reflections. You should be aware that the Class 4 lasers are the most commonly used in the training labs at Coherent. The greatest safety concern is with eye protection. Because a laser beam can be many thousand times brighter than the sun, laser exposure to the eye of only a fraction of a second can permanently damage it. The three areas of the eye that are most susceptible to laser damage are the cornea, the lens, and the retina. The cornea is a transparent tissue layer covering the eye. Damage to the outer cornea may be uncomfortable and painful, but it will usually heal. Deeper layer cornea damage, however, can be permanent. The lens focuses light to form images on the retina. With age, the lens becomes cloudy and can eventually progress to opaqueness. This condition is known as cataracts. The retina is a relatively small area that provides the most detailed vision as well as color perception. A part of the retina that provides the most acute vision is called the macula lutea. To be more specific, the fovea receives most of the image from the lens. Different wavelengths damage different parts of the eye. Wavelengths in the mid and far IR as well as the mid UV affect the most outer layers of the eye or cornea. The near UV wavelengths that fall in the range of 315 to 390 nanometers will damage the lens. The most dangerous wavelengths to the eye are the ones that are focused onto the retina. This range is called the ocular region and includes both the visible and near-infrared range, which is 400 to 1400 nanometers. The lens has a focusing capability of 100,000 times, so it is easy to understand why even a low-power beam can produce catastrophic damage to the eye. One common misconception is that bright light does the most damage to the eye. But this is simply not true. As you can see from this graph, the green light is perceived to be the brightest. However, when looking at the faint appearance of light that has an output of 800 nanometers means you only perceive 1 to 2% of the actual beam. Higher power laser beams of light exist at even higher and lower wavelengths and are invisible altogether. The misperception of output power from the laser is one of the most reported causes of eye injury because your eye's blinking reflex to bright light only occurs for a narrow range of the spectrum. To illustrate this hazard, the first color graph shown represents a uniform intensity of the visible light spectrum. Now compare this to what your eye actually perceives. As you can see, both ends of the spectrum fade away even though the actual intensity remains constant. There are many types of safety glasses available that will protect your eyes from the laser beam. However, there are careful considerations that must be addressed when choosing a suitable pair. As was stated earlier, first and foremost, the eyewear must be suited to the wavelength and be able to handle the intensity of the laser. ANSI Z136.1 standards require that all laser protective eyewear shall be clearly labeled with the optical density value and wavelength for which protection is afforded. The optical density or OD parameter listed on the eyewear represents the degree of protection. Depending on the OD, a laser beam can be partially blocked, allowing the user to see the beam as is shown with this demonstration of a Coherent Sabre argon laser. On the other hand, if the OD is high enough, the eyewear can completely block the laser beam altogether. Notice that the green laser of this Coherent ring laser is able to pass right through the optic, while the red beam is eliminated. By using such a high optical density, you run the risk of not knowing where the beam is and inadvertently crossing its path. The main concern for skin damage are the beam's penetration, the exposure limits, and the size of the exposed area. It is best to avoid moving into the beam's path at all times. Depending on the strength and size of the beam, injuries can range from a slight burning sensation to actual vaporization of the skin tissue. Different wavelengths of the laser light affect different layers of the skin. Some lasers actually pass through the initial layers and damage the tissue beneath the surface. The following graph illustrates the ability of various wavelengths to penetrate different layers of the skin. Keep in mind that the laser beam of any wavelength can burn through all layers if the intensity is high enough. Reactions induced by lasers can cause hazardous particulate and gaseous byproducts. An example of this occurs in material processing such as laser welding, cutting, and drilling from a high-power CO2 laser, like the coherent diamond laser. The vaporized material can create potentially hazardous fumes and vapors and can quickly lead to asphyxiation in a closed room environment. General ventilation safety procedures should be used when lasers are used in this manner. Chemical hazards can even exist with the laser itself. Lasers like the coherent ring laser, for example, use carcinogenic dyes to produce the beam. There are other hazardous chemicals to be aware of that are found around the laser as well. Chemicals such as methanol and acetone are often used for cleaning the optics and are a skin and eye hazard. Therefore, appropriate precautions and protective eyewear and clothing must be used when handling, storing, and disposing of these chemicals. The most common fire hazards are created by using improper beam enclosures that melt or catch fire, electrical circuits shorting out, and the ignition of gases from the process. To minimize these risks, make sure that you are using properly rated equipment and inspect for damage regularly. It is also very important to have a fire extinguisher device near the laser equipment. Whether it is a sprinkler system or a handheld device, be sure that it is rated to do the task at hand when called upon. While the laser beam can blind you, the electricity that is present can kill you. Lasers in general are inefficient at generating laser power and must consume large amounts of electricity to produce a beam of light. For example, high-power lasers like the coherent Saber motor Fred uses three-phase line power, and lethal electrical potentials exist throughout the power supply and laser head. Agencies like ANSI and OSHA set standards that require all electrical hazards have appropriate warning labels and that access to these areas are interlocked. It is for this reason that coherent products comply to these standards and have appropriate warning label designations. In any work environment that incorporates laser technology, various administrative control measures must be employed to conform to safety regulations. In addition to assuring the availability of protective eyewear, administrative control measures such as installing signs with warning lights over access doors that contain laser workstations will be required. In addition, you will also notice that all the training labs at Coherent have posted standard operating procedures that govern safe lab conduct. All individuals working in these areas are required to learn and abide by these rules. Another type of control measure is called an engineering control measure. Engineering control measures are achieved by designing automated safety responses into the laser itself, such as a door interlock. Many coherent laser product lines incorporate an external interlock switch that is designed to shut down the laser when the door to the room is opened. Another type of engineering control measure would be to replace windows to a laser room with special glass that prevents exposure that is similar to the protective eyewear shielding. Coherent strongly recommends using engineering control measures whenever possible. Everyone working around lasers may not be safety conscious. Even when they are, accidents still will occur. The following are some tips to minimize the risk of injuries in a laser environment that may or may not be your fault. When entering a room that has a laser, never assume that the laser is off because the outside laser warning light is off. Before opening the door, be mindful of where the laser is and first look away from that direction as you open it. This may give you the time necessary to back away from a stray beam or for the operator to turn off the laser in time. Never assume that the laser warning light will deter other people from opening the door. If possible, lock the door and always notify others in the area that you will be working with an exposed beam. If possible, prevent others from moving into the beam's path by blocking access with appropriate barriers such as warning tape. Also, be sure to minimize the path and always use proper beam blocking devices. Be sure to remove any unnecessary equipment from the area and make sure that you have sufficient lighting. Common sense will tell you that you do not want to be bumping into things or tripping over power cords when accessing a laser beam. Gold is one of the best laser light reflectors, and it is required that you remove or cover all rings, jewelry, watches, and any other metal accessories that you are wearing that could possibly reflect or scatter the beam. Removing these metal objects is also required when working with electrical components, as the majority of these items are conductors and can pose an electrical hazard as well. The intention of this video was to give you a basic understanding of how to create and maintain a safe laser environment. For additional information on laser safety and the terminology used, you may wish to refer to the following publications and websites. This concludes the laser safety training video. You should now have a general understanding of laser safety and the proper precautions to maintain a safe laser work environment. If you are viewing this video at Coherent and have questions or difficulties, contact your instructor that has presented this video. Otherwise, contact the Coherent Technical Support Hotline. Now that you have had a chance to view this video, please answer the quiz that is included on the CD and submit it to your instructor. If you are not at our facility, please email, fax, or mail the quiz to the Coherent Documentation and Training Department. You must correctly answer 70% of the questions in order to receive a successful completion certificate of laser safety training, and is required prior to attending any class. For those students that plan on attending more than one laser training course, please note that this laser safety certificate is only valid for 1 year.